Hi everyone. So continuing our discussion of measures of central tendency and spread from last week, this week we're going to look at the measure of spread that applies to our so-called normal or standard distribution, right? So that's the bell curve. We talked about skewed distributions, and when we have a skewed distribution, we always want to be looking at the median as the measure of central tendency because it is not distorted by outliers. By contrast, if we happen to have one of these sort of bell curve shaped data sets, we are able to use something called the standard deviation as the measure of spread. We'll obviously use the mean, that arithmetic mean, as the measure of central tendency. And the reason why it's valuable to look at both of these things, although obviously the times that we encounter a standard distribution are going to be fairly few, is because there are special properties associated with the standard deviation and with something called the z-index or c-score that can be calculated that gives us the ability to do some pretty powerful comparisons between what might seem otherwise kind of unrelated data sets. So again, this is also just sort of for completeness. These are both kind of key methods of understanding data sets, and so something that we want to just make sure that we cover. So once again, I'm coming here and I'm going to do a paste special on my data for both values and to transpose it. I'm working with total arrests. Obviously, each of you is going to be working with something different. And I am going to go ahead and actually leave my, I'm actually going to leave my data unsorted in this case, because remember, for the mean, of course, I don't need to have sorted data. Now let me just, before I go any further, let me go ahead and pump up the font here. Apologies, I sometimes forget about that. So let's go up to 18 and see how we do. Okay, so again, we keep our program year because we want to have it on for reference, and we've talked about all of the caveats with this data. So the first thing that I want to do is I want to label my mean, and so gotta make this all the same size as well. I'm going to calculate my mean, which of course we know is very straightforward to do. I can just say equals sum, and then select the relevant data cells, right? And as long as I close this, and now I'm going to divide by the number of data points that I have, which is 19, and there's my mean. Now, the standard deviation is actually a unit, okay? So when you say something is one standard deviation away, it's like saying something is it's like saying 1 inch away or 1 centimeter away or 1 mile away, right? It's a measure. But the numerical value of that measure changes depending on the data set, okay? So basically, one standard deviation for one data set is not going to have the same numerical value as the standard deviation of another data set, but the relationship between that standard deviation unit and the particular data set overall, more importantly, the distribution of data within that data set is always going to be consistent. So what do I mean by that? Well, if you think back to our discussion of quartiles, one of the things that was special and sort of important about quartiles was this relationship, right? Quartiles, we know that what we're doing is literally dividing our data into quarters, right? So we know that between the lowest data value, that 25% of the data values are contained between the lowest value and the Q1 measure, that between Q1 and the median is another 25% of the data values, and that between the median and Q3 is another 25% of the data values, right? So we have this relationship between the number of the data values in a particular data set and those quartiles, right? That's in fact how we locate the quartiles in the first place, is by counting the number of entries that there are and then finding the midpoints, the relevant midpoints to divide it up into quarters. Now, the standard deviation, again, although it has different numerical values across data sets, also has a special relationship to the number, the percentage, the volume of data points that appear within that unit. So what do I mean by that? If we come back to this image, again, this symbol is the symbol for the symbol here is the symbol for a standard deviation. What this is showing us is that when we have this bell curve, this standard distribution, we have between the mean, right? If we go one standard deviation on either side of the mean, we know, and this is a property of a normally distributed data set, of a standard distribution, we know that we will find 68.27% of all of the data values in that data set will fall within one standard deviation of the mean, okay? So that's the way in which a standard deviation also lets us say something about the quantity of data points that appear between two particular numerical values, right? So what our task is to say, okay, we can find the mean, that's pretty straightforward. When we find the standard deviation, we can then look at a data point and we can talk about how many standard deviations away from the mean it is, right? We use it as a unit, as a denominator. We actually use that standard deviation as a numerical measure, as a denominator, to say how far away is this particular data point from the mean in terms of standard deviations. Why would we want to do this? Well, again, just the way we have the upper and lower bound when we're dealing with the median, what this does is it helps us understand how extreme a value is. So, for example, because we know that 68.27% of all data values are going to fall within one standard deviation of the mean, that means that if we find that if we find that a given data point is less than a standard deviation away from the mean, that it's, reasonably typical, right? Not that unusual, kind of part of the central trend. Whereas if we see that it is like 3 or more standard deviations away from the mean, whether positive or negative, that's a really unusual number. In fact, if you add these up, that means that it's that less than 1% of the data points within our distribution are likely to have a value of more than 3 less than 1% of our data points are going to be more than 3 standard deviations away from the mean, okay? So again, that the number of standard deviations that a reading is away from the mean, that a particular data point is from the mean, is what we call the z-index or z-score, and again, gives us that sense of extremity, okay? So it just happens that because standard distributions are symmetric, that we can actually kind of create a unit as opposed to just talking about this as a specific number, okay? So that's what we're going to do today, is we're going to look at how to calculate the standard deviation. Now, it will probably come as no surprise to many of you that we don't actually have to, when we want to find the mean, we don't actually have to write out the formula ourselves, okay? So as it happens, we have a function in Excel, which this didn't work. I actually hate using the built-in functions for this reason. Okay, I can select this, and big surprise, this is actually going to give me the arithmetic mean. Oops, come here. Okay, so what you'll find is that a lot of the things that we're doing, yes, exist in Excel. However, the purpose of our doing this exercise, as tedious as it may seem, is to understand where these measures come from, right? Because it doesn't do us any good to start talking about z-scores and standard deviations and all of this stuff if we don't understand what the actual meaningful implications are of those measures. So how are we going to go about finding the standard deviation? Well, we're going to follow a formula, so this might give you all bad flashbacks to word problems, but bear with me here. This is actually just from the Wikipedia page, and I actually really like this example because what we're going to do is we're going to dissect this sentence, and we are going to use that as a way to actually go through the mathematical process of calculating the standard deviation. So the sentence that I want to draw your attention to is this one. And then we're going to go through it together. So it says for a finite set of numbers, so in other words, just for a finite set of numbers, which we obviously have, we have 20 readings or 19 readings, the population standard deviation, okay, so the standard deviation is found by taking the square root of the average of the squared deviations of the values from their average value. So that sounds like a mental Mobius strip. what we're going to do to calculate this is we're actually going to work backwards through this sentence with our data and show how actually once you start breaking this down, it's quite straightforward to do. It's arithmetic, but it's important that we approach it as a set of steps. Otherwise, we're never going to get anywhere. So I will come back in just a moment and we'll actually set about doing this math. Okay, see you all soon.